last week we kind of left off talking about nonlinear reachability. And we were talking about how it's kind of harder for nonlinear systems than it was for linear systems because we end up with these sets that can be like non-convex, and we need to, it's much harder to work with them. And so what we ended up doing was just showing a whole bunch of different ways to over-approximate these sets. And so we came up with these things where we were passing intervals through these nonlinear functions. So we had like interval arithmetic, and then we showed for these more complex functions, we need something called inclusion functions. And so we started with the natural inclusion function, which was just the thing that allowed us to replace every single elementary function in our nonlinear function with the interval counterpart. But we showed that that worked kind of poorly. So we saw, like, when we applied it to the inverted pendulum, the reachable set quickly got really, really big to the point where, like, we couldn't really say anything about the safety. So then we were like, okay, we need to do something better. So we went back to our calculus class and we remembered the mean value theorem. And we came up with this mean value inclusion function, and then we saw that that did slightly better, at least for a little bit, but then in the end it still ended up kind of blowing up and we weren't able to show safety. And then we saw that those were kind of just special cases of this general thing called a Taylor inclusion function, and so we showed how we could kind of go up to higher orders, but we left off last week and we were still having this problem where it's still kind of blowing up, we still have too much over-approximation. And we were all kind of annoyed that when we were doing everything with intervals, we could only get hyperrectangular sets out because we input an interval, we get out an interval, and then we take the Cartesian product of those intervals and we end up with a hyperrectangle. And so all we could get was hyperrectangle, even though it looks like this set, a hyperrectangle wouldn't fit necessarily very well. And so I kind of left you all hanging over the weekend. I'm sure this is all you could think about, and you're just in major suspense about how we were going to possibly deal with this and not have hyperrectangles anymore. And so that's where we're going to pick up today. Okay, so as I said, last week we talked about interval arithmetic, and then we talked about inclusion functions. And then I told you at the very end, there's this thing called Taylor models that will allow us to not have just hyperrectangular sets. So the idea here is that inclusion functions, no matter how high the order, so even if we have a 10th order Taylor inclusion function, we're still only ever going to output a hyperrectangular set. And so then now we're going to talk about this thing called Taylor models, which allows us to represent much more expressive sets. But before we get into that, I just wanted to follow up from last week. So I really wanted this mashup of Taylor Swift and Taylor inclusion functions, and ChatGPT wouldn't give it to me. But given the advice we got last week about how to do this, was able to create an image of a person who looks like Taylor Swift, is not Taylor Swift, just has very similar features to Taylor Swift, and is now in a mashup with a Taylor inclusion function. So here you go, thanks. Okay.
Well, I sort of like a DNA helix on the right of the first one.
This one, or this thing?
The one that pops.
This thing.
The one on the top. Right. There's a DNA helix. How does that
work? This thing.
Yeah.
Yeah, I mean, similar to Taylor's series, it's all math and science. I don't know. Yeah, this also doesn't really say, it says kind of Taylor inclusion. Yeah, I don't know. They haven't quite figured out how to write yet, I guess. So.
Yeah, well, generally, image generators can't read, so.
Yes. Anyway, there you go, in case you were really looking forward to that mashup as I was. Okay, so back to Taylor models. So Taylor models are basically this thing where we say we have some input set now, so it doesn't have to be intervals like it had to be before. We can have just kind of an arbitrary set here. And we're going to say a Taylor model. We're going to apply a polynomial to this set, and that polynomial has a specific meaning, which I'll talk about in a second. And then we're going to add on some value alpha that comes from an interval. And so the idea here is that the polynomial is actually just the Taylor polynomial of degree n-1. So if we have a Taylor model of order n, we're going to use the Taylor polynomial up to degree n-1. And then the alpha here is just an interval remainder. You can kind of think of it like a remainder, which I'll explain in a second. So the Taylor polynomial just looks like this. It's just the terms of the Taylor model or Taylor polynomial up to n-1. And then the interval remainder, which I'm not like deriving here for you or anything, I'm just telling you that this works. It involves actually kind of the inclusion function for the nth derivative of the function. So we're basically passing intervals through the nth derivative, and that gives us the remainder. And sometimes this is called the Lagrange remainder. And what's kind of cool about this is the way that you can really think of it is, so Taylor models, as you hopefully learned about in calculus, those are things that can approximate the function. So like, the more terms you have of your Taylor model, the closer you get to approximating the actual function. So you can think of this polynomial as giving us an approximation to the function that we're trying to pass our set through. And then there's like some remainder, there's all those higher order terms that we're not including. And so what this kind of interval remainder does is bound the error that we could have in our approximation. So it's saying this polynomial approximates the function as best we can, and then we're just going to add on this interval at the end to bound all of the rest of the error that we could have. So that way we still know that no matter what, our output set is going to be an over-approximation of the points that could actually be reached. Any questions on that? Yeah.
Why does alpha live in some interval alpha? Like the bounds, it's like bounded somehow, but like what is this interval alpha in which alpha lives?
So it's this particular remainder term. I didn't derive how you actually get that. So this is like requiring creating this like inclusion function and whatnot. That's all we're going to do. There's actually ways where you could, instead of passing an interval through this, you could pass like a zonotope through it so that you get a tighter bound. We cite that in the book, but we're not actually going to like get into it. Yeah.
And this is a sort of a natural interval. When you're doing the Taylor series, all the f's are approximated by the natural interval.
So
what is like, you see how you have like bracket f of, like at the nth derivative of f? Yeah.
This is the natural inclusion function for the nth derivative of that, yeah. Okay, and so one thing that's kind of cool about this is it turns out, and maybe you can stare at it longer on your own time to see that this is true, but it turns out that if we just replace this p of x here with the natural inclusion function for the polynomial, so we just pass an interval basically through this p of x instead of passing this arbitrary set that we're going to pass, we just recovered the Taylor inclusion function. So basically the idea here is like, we want to pass arbitrary sets now through these functions, but if we were still passing intervals through them, and we just pass an interval through this Taylor model, we actually get the exact same thing we would get if we used the Taylor inclusion function. But the idea here is that we don't have to do that anymore. So Taylor models provide increased flexibility by allowing us to pass like other types of sets through the Taylor polynomial. So in the linear reachability lecture, we saw how we could pass all these kind of polytopes through different functions, and hopefully we would want to be able to do the same thing here. And so now we can kind of do that. Okay, so here's kind of what this looks like. So I'm showing the same function that we've been working with for a while, but with a different interval this time. And you can see kind of as we increase the order of the Taylor polynomial for the Taylor model, then we get better and better over approximations. At the beginning, it's not so great, and it turns out actually for a zero order Taylor model, maybe this is an exercise you can do on your own time, you'll see that it actually just reduces to the natural inclusion function. A first order Taylor model just reduces to the mean value inclusion function, so we've actually added like nothing interesting yet. But then if we look at the second order Taylor model, this isn't a hyperrectangle anymore, this kind of shaded purple set. It's now actually a polytope, which is great because that was like our whole goal. We can now get like polytopes out. We don't have to have these hyperrectangles anymore. And third order, it's actually kind of hard to see, so I'll like kind of get rid of all the other lines that are there. The third order set is actually like this non-convex, smooth, like funky shape here. So the idea here is like after second order, we're actually able to get sets that become non-convex. Yeah.
So what stops us from doing like, 50th order? So it's just the point estimate kind of, right? The P of X is just like a line, I guess.
Yeah. So the fact that the set becomes non-convex, like we can make this third order thing and it's nice in 1D and I can plot it and see what it looks like. But in general, like non-convex sets are really, really difficult to work with. So even going to third order is like typically pretty difficult for like anything higher than 1 dimension.
Okay, well, yeah. I guess the math is kind of straightforward, right? But then working with it somehow.
Yeah, so then it's like, okay, I have this set that's like this 15-degree polynomial plus an interval, and I want to know if it intersects with this other set that's like a 15-degree polynomial plus an interval, and like that's not an obvious operation to do.
Doing operations on the set.
Yes, exactly. Yeah, and like in general, we're computing these reachable sets, and then we want to like check if they intersect with some bad set or some avoid set, and so if we like, we need to be able to do those operations. Yeah. Yep.
So just trying to get more of like an intuitive understanding of this. So like, so when we're passing in other types of sets into a Taylor model, does that mean like we're kind of trying to do like the multidimensional thing with like a Taylor expansion, but now with this other type of set? I guess like because I guess like I don't know if that makes.
Yeah, I think that's generally right. So here it's a little bit easier in one dimension because we don't have to pass these like multi-dimensional sets through things. I'm going to show an example in a second where we do like higher dimensional things. But here, like literally all we're doing is we're computing the second order Taylor polynomial. So we'll have like an x squared, an x, and a just constant term in there. And then I'm just adding plus or minus alpha to it. So this is just like a function, and then we just got like some width to that function, basically. In this case, since it's one-dimensional, we're still just passing in an interval. But I'll show in a second how we go to higher dimensions. All right. So yeah, so like we were just saying, kind of both questions touched on this, which is like the third order one, it's kind of difficult to represent. It's non-convex. We typically can't do a lot with it. And so where this becomes really useful is in the second order one, because we did get this nice polytope that was no longer a hyperrectangle, but polytopes are pretty nice. They're convex, and we know how to do things with them. So it turns out that this one actually even has like a special name, and that is conservative linearization. So let's talk about that for a second because it'll become more clear why it's called conservative linearization. But it's just another name for a second order Taylor model. So now let's imagine that we aren't just in one dimension like we were before, and now we input some vector x into a function and it outputs another vector. So that'd be like our reach function, we input the state, it outputs another vector, which is the state. And so what we're going to do, just kind of similar to what we did before with the reach function, is we're just going to break it up into subfunctions. So f1 is going to output the first component of the output of this function, and then fn will output the nth component of this function. And the reason we're going to do this is because now we can think about what would happen if we grabbed the first order Taylor polynomial. So again, we're doing a second order Taylor model, so we need n minus 1 for the polynomial, so we're going to do the first order. And so we're going to grab this first order Taylor polynomial for each of these subfunctions. So we'll get like f1 of the center plus the gradient transpose times x minus c, and then so on all the way up till fn. And now all I'm going to do is like rearrange this a little bit. So I'm going to put all of these in one vector and just call it f of c. And then I'll keep all of these in one vector just stacked on top of each other. And then, or this will actually be a matrix, and then times our x minus c. So all I did was rearrange here. And then it turns out this is called the Jacobian, which you may remember from some of your math classes. We call that capital J. And so basically then what we get here is we get this really nice formula, which is just kind of a linearization of our function, first order. So we start with evaluating the center plus the Jacobian times x minus c. And then for the Taylor model, we have our interval remainder that would go with it. And so what's cool about this is that this is a linear function. And we were just doing all this stuff with linear reachability a week ago, where we found out and we actually know how to like pass polytopes through these linear functions. So now we could actually start with an input set that's a polytope and pass it through this function using like our addition and our matrix multiplication that we learned how to do last week. And then we can get kind of a polytope out instead of having to get these hyperrectangles. So that's all we're going to do here is we're going to say that the Taylor model is just, we're just going to replace basically our addition with the Minkowski sum and then do our matrix multiplication. Okay, and then like if you want kind of an intuition here, if you like lost me along the way, the idea here is like we just like linearized our function. We're going to pass a set through the linearized portion because we know how to pass sets through linear functions. But we linearized it, so there's some amount of error there. And so we just need to calculate what that error is and add it on. That's all that's going on. Yeah.
know you said this again. You said about game-free state. Is it the Jacobian of F or the Jacobian of?
Yeah, it's the Jacobian of F. Yeah, so if we go back here, we just get like all these gradients stacked together. Yeah, no worries.
I have a hard time estimating how complex our, let's say, function f or our actual system we're looking at, like what type of model we can still get away with using something like this, and at what point we have like no chance of, doing anything reasonable. So I don't know. For example, let's say the Katz system from the projects, is this like the level of complexity where this would work well?
Yeah, well, so I think, let me go forward again here. So because we're like getting a linearization of the function, like if the function is super nonlinear, then you're gonna have a huge amount of over-approximation, or like this error is not gonna, or this function's not gonna approximate it very well if the function's super nonlinear. So you're gonna end up with a huge interval remainder, and then you're gonna get this hugely over-approximate set. One thing though is like any function is like kind of linear if you like zoom in enough, right? And so we're going to learn about something at the end of this lecture where we can like make these kind of input sets smaller such that this linear approximation holds better. And then I think the scaling is much easier.
Because, for example, even for the theory of Taylor approximations, the theory is like, oh, you can approximate any function on the entire domain of all real numbers, and then in reality, you're like, okay, but we just always do like a linear fit, basically, or maybe a quadratic fit. So like the kind of, I think it's just difficult for me to kind of look at a real system and kind of estimate will Taylor models work here or not. But yeah, maybe I should just try it out.
Yeah, well, no worries. Project 3 is coming up. Okay. We'll give you the chance. Okay. So, and of course, Julia handles all of this beautifully. So, we can just take our Jacobian and then here's that equation that I was showing there with the Minkowski sums and everything, and Julia just does it. Okay, so let's see if this fixed our problem. So back to it. Now we're going to try conservative linearization here. Okay. Ooh, pretty good. Okay. So this is looking a lot better, right? So here, if we go back, here was the Taylor inclusion. We had to get this nice hyperrectangle, conservative linearization. Now we can get this like really tight polytope bound. But since you all know there's more methods coming up, you probably anticipated this. So yeah, we still can't verify safety even with this because it still ends up kind of blowing up at the end here. Okay. Okay, so that was Taylor models, and now we're going to see how we can do even better doing something called concrete reachability. So the idea here is let's just look at this top row for now. So let's say that we're starting with some initial set, and we want to compute our reachable set at time step 3. So one thing we can do, and actually this is what we've been doing, I just haven't really explicitly called it out, is we could just take the set at time step 1, call our reach function that takes in the state at time step 1 and the disturbances for the next time steps until we reach time step 3, and then use that to get our set at time step 3. And in the process, we never really care about what the reachable set at time step 2 is, or at least not explicitly. It'll kind of implicitly get calculated as we do this, but we never like explicitly create that set. So we're kind of just starting from 1 and skipping all the way to 3 using this rollout function up to 3 depths. So this is like what we've already been doing this whole lecture. But there's one thing that we could do instead, which is we could do this thing called concrete reachability, where now if we start with our reachable set at time 1 and we want to get to the reachable set at time 3, we can just look at one step at a time. So we can say, okay, we're just going to start from S1, take the disturbance for like that single step, that gives us R2, and then we kind of fully compute an over approximation of R2, and then we use that to compute R3. So now we say, okay, we'll start from any state in R2, take another step, and then compute the reachable set at R3. And kind of the idea here is that we say we concretize the reachable set at every time step. So we're concretizing the reachable set at time step 2, whereas here we're just saying time step 1, here's a function that gives us the reachable set at time step 3. I'm just going to use this function and not care about what happens at time step 2. Here we're like explicitly computing it and then using it to compute the next one. So this is more similar to like what we were doing with the set propagation stuff in the linear chapter. Okay, so it's kind of a subtle distinction. So are there any questions here? I'll pause for a second. Okay. Okay, so let's talk about why we might want to do one versus the other. And there are like trade-offs, so sometimes you do want to do one and sometimes you want to do the other. Okay, so one option, or one trade-off for symbolic reachability is that it can be quite computationally expensive, because when you do symbolic reachability algorithms, they're considering the entire rollout function at once. So if we want to go from time step 1 to time step 10, we're looking at the rollout from 1 to 10. So like all this stuff, every single step inside of there is being all kind of wrapped up into one function. And then we need to take like gradients and Jacobians and whatnot with respect to that if we're going to do these inclusion functions, and that can be computationally expensive. Another similar thing here is that because we're using this kind of entire rollout function, as we talked a little bit about last lecture, the nonlinearities that are present in all of our various models will compound over time because we're getting them for every single time step. So those are two issues. One thing that's nice is it doesn't have an issue with the wrapping effect, and you're like, what the heck is the wrapping effect? We haven't even talked about that. It's a thing that concrete reachability has an issue with, so we'll get there in a second. Okay, so concrete reachability, more computationally efficient, because now we're just doing one step at a time, so we only have to consider like one step of our system when we're taking gradients and all that stuff. We don't have this issue of compounding nonlinearities because we're just doing the nonlinearity that's in like a single step every single time, so that can decrease the amount of over-approximation. But you do have this thing called the wrapping effect, which is basically error from concretizing the reachable set at every single time step. So if we go back here and we look at this, at time step 2, we concretize like an over-approximate reachable set for time step 2, and then we use this over-approximate set to compute the reachable set at time step 3. And so we're including a whole bunch of starting points at time step 2 that probably aren't actually part of the reachable set. But because we can only get this over-approximate version, we had to do that. And then this kind of over-approximation error will compound over time, and it's called the wrapping effect. Okay, now we're going to have to click through all this. Yeah.
Why is this any different than the previous approach, in the sense of you just run the previous approach up to a smaller horizon and then look at it and then keep running?
That would be this. So this is, well, so I'm saying do it at every time step, but you could do a mix. You could do like 3 time steps, concretize, another 3 time steps, concretize.
But I guess maybe what I'm not quite sure is like, what does it mean to concretize in the sense of, like, conceptually, not in like how to do it mathematically, but you have a set that you're propagating in either of these cases. Why is it the one suddenly to shrink the bound?
So when you propagate, let's say I want to go from time step 1 to time step 3. Then I'm going to call the step function twice, right? And then the function, so then let's say I want to use like a Taylor inclusion function. So now I'm going to create a linear approximation of that. And I'm going to create a linear approximation of the rollout function for 2 time steps. And then that will give me my reachable set at time step 3. If I want to do the concrete version, then I'm going to start with the one for the initial time step. I'm going to linearize only one step of that function. Then I'm going to get an actual set out for that. And then I'm going to pass that through the linearized one-step version again. Does that make sense?
Like, naively, it doesn't seem like those two would be that different, and in particular, it doesn't seem like contributionability necessarily gives us a smaller set.
It doesn't necessarily give you one, but sometimes.
Okay. Got it. Okay.
Yeah, which is actually going to be like my next point. So whether symbolic or concrete reachability will perform better is very much problem dependent. So like, maybe if you're really worried about these compounding nonlinearities, which turns out, like, surprise, surprise, is going to be the case for the pendulum, then concrete reachability might be better. But if you're concretizing into some big over-approximate set, then the wrapping effect is going to be a major issue, and then maybe symbolic will be better. So it's not always obvious. And like I just said, people tend to like combine these, so maybe you do like a few symbolic steps, concretize, do a few more symbolic steps, and so on. So you can kind of trade off between these things. Okay, let's see if this fixed our problem. Okay, so now we're going to do concrete conservative linearization, and you can see there's no more options, so let's hope that this works. Okay, here's one step. Yay! Okay, so now we can tell that our system is safe. We're nowhere near the avoid set, and we've got this kind of really nice tight bound, even 14 time steps out on the reachable set.
And this is using the previous reachability version together with the concretization.
Yeah, it's using the conservative linearization with the concretization. Yeah. You can make any combination that you want, though. Yeah. Sure. So so let's say, imagine let's say for step 14, so this step here, when we do this version of things that had this crazy over approximation, we're considering the rollout function through 14 time steps. And so when we linearize that, we're trying to linearize this function that's like got nonlinearity after nonlinearity after nonlinearity, because we keep applying that nonlinearity in the step function. And so you could imagine that that's probably not going to work so well, because we're trying to linearize like a very nonlinear function, and then we get this huge amount of over approximation error. Versus when we do it from this one, we're starting with the set at time step 13, and then we're saying, let's just take one step, linearize just that one step, so that's going to be less nonlinear. If you remember, the pendulum only has sine in it. That's the only nonlinearity. So then in that case, we start with this small set, we don't have too much over approximation error, and then we just make one step, and we get a smaller one.
Kind of effect that we're trying to do over the full time step length. But then I guess we don't see the wrapping effect here.
The wrapping effect didn't end up being too bad.
Oh, okay.
So you can imagine, let's say that instead of doing the concretization on the conservative linearization, and instead I did it, say, on the Taylor inclusion function, then now when I compute the reachable set at the next time step, I have to take this entire rectangle and use that as my starting set for the next time step. And so I'm going to get all of this extra states that probably aren't in our reachable set, but we don't know for sure. And that's going to compound over time. And so then the wrapping effect probably would be a lot worse. So yeah, it's not always clear. There's a really nice discussion in the book of it that I recommend checking out, but it's not always clear which one is going to be better or which one's going to dominate. Okay, but can we do even better? Yes, we can. So this last thing that we're going to talk about today is partitioning. And so here's the idea. We already kind of talked about it a little bit earlier. But basically with partitioning, what we're going to do is we have some initial set. And then what we do is we partition this initial set into some smaller set of subsets, such that the union of them will give us our original set. And then we're just going to do the reachability for each subset. So I'm going to pretend just starting in this purple set, what is the set of states I could reach starting in the blue set, and so on. And then we get these sets over here. And then all we have to do is take the union of these sets, and then this gives us an over approximation of our reachable set at the next time step. And you can do this for however many time steps you want to do this. And so you might be thinking, okay, why would we do this? And we already kind of talked about it a little bit in response to one of the questions earlier, which was that propagating smaller sets tends to result in less over approximation error. And the idea there is when we try to linearize a function, for example, depending on what algorithm we're using for this propagation, if we're trying to linearize, then a smaller set is going to be that linear approximation will be closer to the true values in a smaller region. Because you can imagine, if you shrink all the way till it's just a point, your linear approximation will match exactly. And so one thing is that just propagating these smaller sets will result in less over approximation error. So that when you take the union of them, ideally you have less over approximation error in total. And then the second thing that's kind of cool is we can actually represent non-convex sets as a union of convex sets. So even though here, let's say I was using the Taylor inclusion function and we could only get hyperrectangles out, we'll get hyperrectangles out for our reachable sets of each subset in the partition, But then when we take the union of them, this is now a non-convex set. So we can represent kind of more interesting shapes if we partition the input space. Any questions on that? Yeah.
I guess also before in the Pluto notebook, the result that you showed looked really good, but also the set was like shaped like a line. So that was a little bit cheating because if you use because actually the most recent inclusion function was basically like a line shape plus some bounds, right? And so I guess with this you could, like if you had some, let's say moon shape or whatever, you would probably already run into trouble. And now I guess with this you can try to like have a bunch of lines next to each other. That's kind of the...
Yeah, that's exactly right. So like if our set in the pendulum was like some weird like, I don't know, dome or something like that.
Sets are like that. Yeah.
Okay, I won't call it weird. If our set was some dome, then then like this might help you out because you could actually like kind of using a bunch of tiny hyperrectangles try to represent that.
But I remember, I think I tried this once, and I think you can get like a combinatorial explosion of, because later you want to do like set intersection or something like this. Yeah. Yeah,
and like if your system is like high dimensional, partitioning is gonna like, if you want to like evenly partition, it's gonna grow exponentially with the size of the that's it.
Is it best practice to partition and then do some propagation, repartition, do some propagation, or keep your partitions?
It's probably problem dependent. I think like there's just a ton of research out there on like efficient partitioning strategies, and people have tried like everything. My intuition has been like, I was gonna try to make a joke about this, but I couldn't think of anything funny. But like, you know how like there's like those things where like people do all this crazy math, complicated whatever, and then like a machine learning model just like blows it out of the water. I kind of feel like that was partitioning. Like throughout my PhD, like we would come up with all these great strategies, and then it turns out like you just partition it, like everything just seems to work really well. So I would definitely like highlight this is a very good strategy, and maybe for project 3 it'd be something worth trying. Okay. So now just so you can see kind of what this looks like. So you can imagine that, you know, the smaller and smaller we make these subsets in the partition, of course the more sets we have to keep track of, but typically the better and better approximation we'll get. So here we go. There you go. I'll play it one more time. So these are the subsets, and then this is the result. Okay, so you can see like now, even though everything's a hyperrectangle, we can very closely approximate this kind of non-hyperrectangular set. Yes.
Is it always easy to like come up with and partitioning a rectangle? I can do it. Partitioning some like strange output shape seems like difficult somehow. Like if you want to maybe partition again this new thing or whatever.
Oh, well, I think what I would do is only partition the input set, which typically is nice, and then like propagate them all the way to the opposite. Yeah. Yeah. So that's it. Yeah.
How many things partition into in one space?
The general rule is like smaller the better. So the more partitions you do, the better. But of course, that's going to like increase your computational costs because now you have more sets to keep track of. So you could be smart. You could be like, oh, I think I'm going to get a lot of over approximation error in this region, so I'm going to make that part really small, and then like these other parts I don't care as much about. Or like, there's like so many things you can do, and there's actually like a ton of papers about people trying to do just this, including some of my papers. So yeah, there's lots of different ways to do it. Okay. And it generally makes really cool looking GIFs. So this was one of my first projects for my PhD, and I think it is what inspired me to make cool animations in the future. So there you go. Okay, that is it for nonlinear reachability. Okay, cool. So we'll switch over now to the third chapter on reachability, which is discrete reachability. So for discrete reachability, so we talked about reachability for linear systems, we talked about reachability for nonlinear systems, those are both continuous. Now we're going to talk about reachability for discrete systems, where we have discrete states and disturbances. And it turns out we can represent discrete systems using directed graphs. So in our graph of a discrete system, we have our states. So this system particularly has two states. So we have S1 and S2, and our nodes in the graph just represent states. And then we'll say like maybe from S1, we have a 0.8 chance of transitioning to S2, or we have a 0.2 chance of staying in S1. And so the edges on our graph are going to be potential transitions that could happen between states, and then the weights on the edges are the probability of this transition occurring. And then similarly from state 2, maybe we have a 0.9 chance of going back to S1 and 0.1 of staying in S2. And in general, it's possible to kind of convert any discrete system into a graph like this. So here's the code that we have in the book. The first line here, we just grab all of the states. So because it's a discrete system, we can just enumerate the states. So in this case, we have the states are like S1 and S2. That's what we had. We create a graph with these states. And then we just go through each state, and we have this successors function, which tells us all of the possible next states and the probability of transitioning to them. So that would give us, this 0.2 and 0.8, and we add them as weighted edges to our graph. Then we go back and we go to the next state, and then we again compute the successors and add them as edges to our graph. So nothing too crazy going on here. It just happens that if we represent discrete systems in this way, we're able to do lots of things to them to kind of do some analysis. Okay. And so then this is our final graph. And we can do this for more than systems with more than just two states. So for example, for the grid world example, this is what the graph looks like. So there's a node for every single square in the grid world. And then there's these edges that represent the transitions between nodes. And in this plot, we have darker edges being like higher probability of transition. So for example, you can kind of see like the dark edge here is to go up, which is the highest probability outcome. And then again, you can kind of see like what the policy in general would be from just the colors of these edges. Okay. Any questions on converting things to graphs? Okay. So with all of that, we can do lots of different types of analysis. So one type is just computing reachable sets from this. Another thing we'll talk about is satisfiability, but super briefly. And then we'll talk about probabilistic reachability, which is kind of cool, something that we haven't done in the other reachability chapters. And then you might be thinking, oh, I'm going to tune out this whole lecture because I only care about continuous systems. Please don't. You can convert continuous systems into discrete systems using something called a discrete state abstraction. So we'll talk about that. Okay, let's start with reachable sets. So let's consider this kind of very simple system here. It's just got a few states in it. And we want to compute the forward reachable set for this system. And so what that means is we start in our initial set of states. So in this case, it's just one state, S1. And then we just go forward one step in time. So we look at all the states that are connected to it with a forward edge going to them. And then those are going to be reachable at the next time step. And then we go one more time step in the future. And then we can just continue to do this to figure out what the forward reachable set is. And you'll notice I kind of dropped the probabilities off of these edges. I dropped off the weights. And that's because when we're just talking about reachability, we just want to know what states are reachable. So as long as there's a non-zero probability of transitioning from one state to the other, we have an edge there. And so all we care is basically whether or not there's an edge at this point. Okay, we can also compute backward reachable sets. And so in this case, we start basically at the target set, so the set that we care about reaching. So it could be the set we want to avoid, or it could be a set that we want to reach. And we start at this target set, and then we're just going to go backwards through the graph. So we're only going to be able to go kind of the reverse direction of edges. So we'll start at the target set, go one step backwards again, and this gives us the backwards reachable set. So nothing crazy going on here. And this process is really just equivalent to breadth first search of a graph. So once we've taken our discrete system and converted it to a graph, we can just do breadth first search, and that gives us the forward and backward reachable sets. Okay, so let's see what this looks like for the grid world problem. Okay, so here's our grid world graph. Not really showing here's all the edges, but I'm not showing any difference in their weight because we don't care about the probabilities right now. And so at the first time step, we just start in this lower left corner. We go one time step into the future, and then these are the two states that we could reach using those edges. And then we can just keep doing this and get the reachable set over time. And eventually everything is reachable because everything in the grid world is connected. So this isn't super interesting. But you could imagine, and I'm going to show later, like for the pendulum, I'm going to show a graph where like everything's not connected. So this ends up being more interesting because you can kind of see over time what states actually end up being reached as we like traverse through the graph. We could also do this again in the backwards direction. So maybe we want to say like what states could reach the obstacle state. So we're starting in the obstacle state, or what states could reach the goal state, starting in the goal state. So then if we go one time step, this is like all of the states that could reach the obstacle state in one time step. Again, nothing crazy. This is like a grid. We could do this in our head, but for more complex graphs, this becomes more interesting. And then this is all the states that could reach the obstacle or the goal in 2 time steps, and so on. And then we could, do this for a while and find out that basically all states could reach the obstacle and the goal. Okay. So one thing that's kind of cool about this, though, is that for discrete reachability, it ends up being much more straightforward to check for invariant sets, because all we have to do is like our sets are just collections of states now, or collections of nodes in the graph. And so to check if like one set is a subset of another, all we have to do is check if like a set of states is a subset of another set of discrete states. And so basically what we're saying here is like if the reachable set from time step 1 through D is a subset of the reachable set of the previous time steps, then we know that R1 through D is an invariant set. We can't reach any more states from it. So let's just do an example here. I think it'll kind of clear things up. So let's say we have this system here, which has 4 states in it. And let's say that our initial set is S2 here. So then R1 is equal to just S2. R2, we go 1 time step into the future. We can reach state S3. That's the only state we could reach. Now we're at S3, we go 1 more time step into the future. We could either stay in S3 or we could end up in S4. So R3 is going to be S3 and S4. And then let's go 1 more time step into the future. We could either stay in S4 or end up back in S3. And so now we can check this property. So we see that R1 through 4, which is going to be all of the states that we've seen here, so S2, S3, and S4, we want to check if it's a subset or equal to R1 through 3. So R1 through 3 is all of the states we've seen so far through here, which is S2, S3, and S4. That is the case. And so now we can say that S2, S3, S4 is an invariant set, and we're going to stay in that set for all time steps in the future. So we had kind of the same thing going on with our linear reachability. I think we talked about this. But the key insight here is just that it tends to be much easier to actually check for these subsets because we're just checking whether points are contained with another set of points. Yeah.
When I was looking at the topic in the book, I had kind of imagined that we would do this by like discrete reachability, but we're setting up like a transition matrix and then taking this matrix to like the infinite power and then seeing which states have like a non-zero probability of being reached. Does that make sense?
How do you raise the matrix to the infinite power?
You take a higher power until the values don't change anymore much.
That's exactly this. So you just keep going until you find this property.
Sure, but the way we do it is like kind of with like a no. Okay, but I guess my question is if these are like basically the same, doing like a for loop over some nodes and then trying to like add to some set versus doing like this kind of linear algebra approach. It's kind of the same thing basically. Okay.
Yeah.
Okay.
Yeah.
Is there ever a case in which we never find this invariant property for finite graphs? Is this a good termination condition for everything we try, or for most things we try?
Well, it could take a really long time to find it.
This is true.
But it feels like you would. I don't know. I can't say for sure. I feel like you would always have this happen. Well, because you could just reach every state or reach all states that are reachable, and then you're always gonna like.
Right, but is there some because we never take a state separate way from the second.
Yeah.
Oh no, we do, right? Because
R1 through 4 will, or like R1 through 4.
Yeah.
So yeah, I think it is the case.
Okay.
Okay. And so one thing that might be cool about this is like now that we have an invariant set, we know we're never going to reach any other states other than S2, S3, S4. So that would tell us that we could never reach S1. So if for some reason we cared about whether or not we reach S1, now we could like make these types of claims. Okay, so super briefly, let's talk about satisfiability. So here I just told you like how to compute the reachable set. I didn't necessarily tell you what to do with it. So one thing we might want to do with this reachable set is determine whether or not we end up in some sort of set that we want to avoid. So let's say in this case the target set is an avoid set. And we can look at this graph on the left, and we can do forward reachability. So we see 1 time step, we could end up here, 2 time steps, we could end up here. And now we've reached an invariant set, we can't go anywhere else from here. And this does not intersect with the avoid set, so we can say that it's safe. Similarly here, now we go and we can see that we could end up here in 1 time step, here in 2 time steps, and then in 3 time steps we can end up at the avoid set, so then we can say that this is unsafe. So basically we just want to check if our forward reachable set ends up intersecting with this avoid set. Similarly for backwards reachability, we could start at the avoid set, go 1 step backwards, go 1 step backwards again, and then we can see that this doesn't intersect with our initial set, and so our system is safe. In this case, we can go backwards 1 step, go backwards 1 step again, and then 1 step again, and we see that it does intersect with our initial set, and so this is unsafe. So basically the idea here is just that for forward and backward reachability, for forward reachability, we start at some initial set, and we check if our reachable set intersects with some bad set, and then for backward reachability, we start at the set we don't want to end up at, we go backwards, and we see if any of those states that could reach the avoid set include the initial state that we expect our system to start in. Okay, so doing this is basically checking satisfiability. We're checking if a system satisfies a property, specifically if it like intersects this avoid set. But one thing that's kind of interesting is like we did that just now by computing the full reachable set. But if we just want to check satisfiability and we don't care about what the reachable set actually looks like, there's much more efficient methods for doing this. So if we're like, we can do it without computing the full reachable set, we can just see if there's like any paths to a bad state, for example. And so there's lots of things you could do here. You could do like heuristic search. For some situations, you can do Boolean satisfiability, SMT, etc. And section 10.3 talks about this, but we're not really going to get into it. But you can check it out in the book if you're interested. Okay, so now we're going to get into this idea of probabilistic reachability. Okay, and so probabilistic reachability, so far we've just been able to say we either reach a state or we don't reach a state, but sometimes that's not good enough, because like for the grid world, we were just like, oh, we can reach all possible states, like that's not very interesting. And ideally, yes, we can reach all possible states, but hopefully like the obstacle, for example, we reach, but we reach with some very low probability. So that's kind of the goal here. And so you might think like, why do I care about this? Why do I want to do probabilistic reachability? Okay, and so I'm going to introduce it with this bet that I have with my husband. So we have these goals or challenges that we've set for each other, and we wonder which one will be reached first. And so the challenge that he has set for me, so he used to play baseball at a pretty high level growing up, and he thinks that there's no way that I could ever make contact with a 90-mile-an-hour fastball. For those of you who don't play baseball or haven't really seen it, here's what a 90-mile-per-hour fastball looks like. It's pretty fast. But all I have to do is make contact. Like the bat just has to hit it. So like, I don't know. And so the question is like, in fewer tries, would I be able to do this? Or if you might remember about me, I used to jump rope competitively, and there's this trick called a triple under, and he thinks that he can do this. Here's what it would look like. So that's 3 times under your feet before you land. So 1, 2, 3. Okay, so he thinks he can do this. So the question is like, which of these would take fewer tries to do? And we have not tested this out yet, although I will say he's about 20 tries deep on the triple under and hasn't gotten there, so we haven't gotten to a batting gauge for me to give it a try. Okay, so let's say though, let's just hypothetically say that we both adopt a policy of taking random actions. So like I'm just like randomly swinging the bat and he is just like randomly turning the rope, and like we'll see what happens. And so a reachability analysis, like everything we've done so far, would just tell us that both these goals are reachable. So I think randomly at some point, like he might accidentally do a triple under, maybe I'll like accidentally hit a 90-mile-per-hour fastball. But if you ask me, like the probability that I accidentally hit a 90-mile-per-hour fastball is like much higher than the probability that he like accidentally does a triple under. Like, right? Like I think the bash is going to hit the ball at some point. I don't know. Those of you who play baseball, maybe you can correct me. With the deterministic reachability, we don't get to know these things. We just say that like it could be reached. So we don't get to know the relative likelihood of these goals. And you know, if I'm going to specify some terms for this bet, I would like to know some of the relative likelihood. So that's kind of the idea of probabilistic reachability. But obviously, this one is more likely to occur because, I mean, you guys have all seen my skills with a baseball bat. So like, clearly, clearly I've got this in the bag. Okay, I'll keep you posted if we ever give it a try. Okay, so probabilistic reachability allows us to understand the likelihood of reaching a particular state or set of states. Okay, and so specifically the first thing that we're going to talk about is probability of occupancy. And so that tells us the distribution over reachable states at each time step. So it's like, what is the probability that the system is in this state at this time step over time? And so we can compute this probability recursively. So at the initial state, or the initial time step, the probability of being in state S at time step 1 is just going to be equal to the initial state distribution. So we just specify what that is. So we say, like, here's the distribution over states that we might start in. And then from there, we can say that for time greater than 1, the probability of being in state S at time t plus 1 is equal to the probability of being in state S prime at time step t times the probability that we transition from S to S prime. Sorry, transition to S from S prime. So the idea is that we look at all possible states. Sorry, we have to sum over these. So we sum over all possible states that we could have come from, and we say, what is the probability we were in that state before, times the probability that we ended up transitioning to the state that we're now at. Okay, so this is basically the formula that we just apply over and over again for this. And so you can see we've implemented it in this algorithm where we keep track of P in some dictionary. We just initialize it to the initial state distribution, basically. And then at every time step, we use our graph to actually do this computation. So the only time that this transition probability is going to be non-zero is if the in neighbor of S, so if we have a state that's coming in, is connected. So basically, we have connections where this transition probability is non-zero, so we can just look at the in neighbors in our graph and look at, compute this formula. Okay. And one thing to note here is like we're returning a probability distribution over states. So all of these probabilities that we calculate, if we sum over S, they should add up to 1. Because basically we're saying at this time, here's like the probability that it's in any of these different states. Okay, so let's see what that looks like. Okay, so here I'm showing a similar thing. We still have the graph. I'm showing the nominal path. So if we had no disturbances at all, this is the path that we would take to the goal. And then over time, I'm going to show, kind of based on how blue it is, will be how likely it is to be in that state. So we say all of our likelihood right now is in this blue initial state. And then let's go 1 time step into the future. And so now you can see we have like most of our probability. It was like most likely that we transitioned to this state up here. But it's possible that we slipped and we stayed in the same state, or we slipped and we ended up over here. Yeah.
So this is some policy as an environment defined something.
Exactly. So this is our grid world. This is our grid world agent. Yeah. So the graph is defined by looking at that policy and understanding if it takes this action and then these are the disturbances, what is the probability it transitions to these other states? Okay, so that's 1 time step. We can take 1 more time step. And now you see it's still most likely that we've kind of followed this nominal path up here. But based on our disturbances, we could have stayed here. We could still be here. We could have slipped over here, with these being a little bit less likely. And then, as we kind of keep going, you'll see that this probability just kind of follows up that nominal path spreading out a little bit over time. And you can see like we do have a chance of reaching the obstacle state, but it's this low probability. So we know that most likely we're up here, but there is this kind of small non-zero probability that we could have ended up in the obstacle at this point. And then we can kind of keep going over time, and eventually we just have this very high probability that we've ended up in the goal state. So by 42 time steps, we've most likely made it to the goal state, and so that's why you have this high probability here. Okay, so that's one thing we can do with probabilistic reachability. But we also might be interested in the probability that a set of states is reached in a given time horizon. So maybe we have some set of states we want to avoid, and we want to know the probability of ending up in them. And so what we can do is we want to compute this thing called R, we'll call it R sub t of S, which represents the probability of reaching a state in the target set in t time steps if we start in state S. So I'm going to give you some state, and I'm saying I have this many time steps in the future. Is it possible, or what is the probability that I reach this target set within that time frame? That's what we want to compute. And so we can again do this recursively. And so the idea here is if we just have one time step, so we only get to see where we currently are, then the probability that we reach a state in the target set will be 1 if we're already in the target set. And if we're not in the target set, we don't have any more time steps, and so it's going to be 0 otherwise. So we start with that. And then we can say for time steps greater than 1, well, the probability that we reach the target set at some point is going to still be 1 if we're in the target set. But if we're not in the target set, it's kind of the opposite of what we were just doing. So we're saying the probability of reaching a state in the target set in t plus 1 time steps from state S is going to be the probability of reaching the target set in t time steps from state S prime times the probability that we transitioned to S prime from state S. From state S. And then we're going to sum over all possible next states. So we're going to say, like, I'm going to look at all the next states that I could go to, and I'm going to say, what is the probability that from that next state I reach the target set, and I'm going to multiply this. Give you a second to kind of take that in. Okay. So here again, it is in code. We're doing a very similar thing. So we have this condition here, and then now we're using the out neighbors of the graph instead of the in neighbors, because we're looking at what we could transition to. Okay, question for you. Will all of these entries in R sum to 1? Stumped you guys. If I sum this over all of S, will it sum to 1? I see a no. No. Yeah, okay, great. It will not. And so the reason for that is this isn't like a probability of distribution over states we could end up in. This is saying if I start in this state, what is the probability that I reach the target set within some time horizon? And so I could have, a 0.9 probability of reaching the target set from this state, and I could also have a 0.9 probability of reaching the target set from this state, and so they're not going to sum to 1. This isn't like a probability distribution that we're calculating. Okay, so let's see what this looks like. Okay, so now I'm going to show it again. So let's say that we want to figure out what is the probability that we end up in this obstacle state. So ideally this should be low for everywhere because we have a policy that's trying to avoid the obstacle. And then what is the probability that we reach the goal? So ideally this should be high everywhere. So I can kind of move this forward in time, and you can see this probability kind of spreading out. So the states near the goal are now very likely to reach the goal within, let's say, 4 time steps. And so on, and then we can kind of just keep doing this over time. And you'll see that after a while, all of these have kind of this very small probability of ending up in the obstacle because we were trying to avoid the obstacle, so that's a good thing. But the ones closer to the obstacle have like a higher probability than these ones out here because they would probably reach the goal before ending up in the obstacle. And then everywhere, there's like a decently high probability of reaching the goal, but it is a little bit higher for states that are near the goal. Yeah?
Why is it that the or maybe just the rendering. Like, why is it the obstacle doesn't seem as like red? The obstacle itself doesn't seem as red than the target seems discrete. Like, are the probabilities of reaching the obstacle the same as the probability of reaching the goal at the goal?
Yeah, I think it's something with the rendering.
Okay.
There should be like a probability of 1, and there should be a probability of 1.
Awesome, thanks.
Okay. So you might be wondering then, like, it kind of looked like after a while it was converging, so we did 200 time steps. So what we could say from what we just saw is that, like, after doing 200 time steps, then we know that within 200 time steps, this is the probability we would have reached the goal, or we would have reached the obstacle from each state. And so if we just look at like the initial state, so we look at the state in the bottom left corner, and we plot what that probability was kind of over the time horizon, it looks like this is converging. So it kind of looks like, as we get to 200, it's around a little less than 0.8 chance that we've ended up at the goal, and a little over 0.2 chance that we ended up in the obstacle. And so it kind of seems like this is converging, and so you might wonder, can we get infinite time guarantees? And so yes, we can. I listed this as an advanced topic, but it just kind of amounts to solving a system of linear equations. So you can check that out in the book. Okay. But some of you are sitting here and you're like, but all my systems are continuous, so why should I care? And the cool thing is that we can actually turn continuous systems into discrete systems using something called a discrete state abstraction. Okay, so here's basically how this works. So let's try to do this for the pendulum. So we have a continuous system. You see the mouse? Yeah, okay. So we have a continuous system that's like this pendulum here. And then we will take this kind of continuous space of states. So we have theta on the horizontal axis, omega on the vertical axis, and we'll basically partition it up, similar to what we were doing at the end of the last lecture. And then each one of the cells in this partition is going to be a node in our graph that we're going to use for discrete reachability. And then we need to figure out how to connect all of these nodes together. And so what we can do is we can just take one of these nodes, and then let's just look at this for now. We can look at the kind of cell in this partition that contains that node. We'll call that S. And we want to connect states to states that are reachable from this particular cell. And we'll over-approximate the set of states that are reachable so that when we do all of these graph operations, we can get an over-approximate reachable set. So now we're kind of sitting here thinking like, okay, how can we determine the set of reachable states from all of the states in this particular cell here? Does anyone have an idea? I feel like Mykel has an idea.
Earlier methods.
Yeah, we could use an algorithm from chapter 9. So we just learned all about how to take, some initial state in our state space and figure out what are the set of states that we could reach from this state. And that was like natural inclusion functions, Taylor inclusion functions, and so on. So we could use any of those and figure out what we could end up in. Yeah. No. Okay. So let's do that with this one. So let's say that we used the conservative linearization. So now we've gotten an over-approximate reachable set of states that we could end up in. And then because we're in this discrete world now, we're going to have to over-approximate it a little bit more. And so we're going to look at all cells in our partition that this next set of states overlaps with. So we're even more over-approximate. And then we're basically going to draw edges from this one to all of those. So this is kind of an over-approximate set of states that could be reached from any state that's in this particular part of the partition. And so then you can imagine that we just do this for all of the states. So we look at this state, this state, this state, and we compute the set of states that we could reach and draw edges between them. And then we get this nice graph that represents the inverted pendulum. And we can kind of abstract away everything else, and we get this discrete state abstraction that looks like all of the discrete systems that we've been working with. Any questions on that? So if you remember the inverted pendulum, it kind of started in that little box and it kind of like slowly moved like that. You remember the set's kind of doing that? If you kind of look, this kind of has that shape. You can almost see that like circular shape there. And I'll show you in a second, actually, after some fireworks. So now we can apply our discrete reachability algorithms to this abstraction to get an over-approximate reachable set, which is pretty cool. So for example, let's say we applied that forward reachable set thing that we were doing on the graphs. We apply it to this. So up here, I'm showing the graph that we're actually doing this on, and then down here, I'm showing all of the cells in the partition that are kind of corresponding to the points in this graph. So we start with some set of initial states. So that's we pick some set of initial cells or initial nodes in our graph, and then we propagate forward through the graph. And you can see eventually here we've now converged to the point where our set is no longer changing anymore. And so now we can say that the reachable set has converged to this, and we don't intersect with the avoid set, so we can say that our system is safe. So we were able to basically take a continuous system, create this abstraction, apply all of our discrete algorithms to it, and then we can bring it back into the continuous space and still make claims about our continuous system. Yeah.
Even though it is discrete, the continuous state doesn't kind of. I guess because right now the continuous one is just the box that we have up.
Oh, yeah. So it's kind of when we were doing partitioning for the continuous one, we were able to get these more interesting shapes. This is kind of a similar deal. Now that we've that might be an advantage to doing this discrete state abstraction, because you can actually get these more interesting shapes out because you're taking the union of these sets. Yeah, I think they do. Well, so you have to do the continuous reachability to figure out what these connections are. So it's kind of you just did this analysis over a bunch of parts of your state space. Okay, I think we're going to finish this lecture. So this is I think this is the last thing. So basically the idea here is a finer partition will result in less over-approximation, as you might imagine. So here's the partition similar to what we were looking at, and then as you get finer and finer, we're able to get this much more interesting, tighter over-approximation of the reachable set. Yeah, that's it. Okay. Any questions? Yeah.
I feel like we needed a lot of methods to even get the inverted pendulum to kind of barely be proven. Do you know if there's real applications that use reachability successfully that are more complicated than inverted pendulum? Maybe also to Mykel.
Yeah, I would say
robot navigation would be one example using pretty coarse models.
Okay.
And then we're also going to have a guest lecture on Thursday, and I'll go through a little bit of the information about it before, but some of these techniques are used to analyze the output sets of neural networks. Not huge neural networks, but reasonably sized neural networks, which is pretty cool. So we'll talk about that on Thursday.